So now let us look at this question. So in this question, you have this 9 kg block that comes and strikes that other 9 kg block which was at rest, but it is not an elastic collision. If it was an elastic collision, things would have been simple. This guy will go and hit, it will stop, and this fellow will start moving at 6 meters per second. Now this is collision with E given, it is 1/3. And now the spring was initially unstretched. So during the collision, the spring cannot get stretched a lot, right? Because, or compressed a lot, because the whole collision is going to get over very quickly. So by the time this guy has not even started moving very much. So that means the spring is not exerting any extra forces. So we can do the collision separately without worrying about the spring. Then we can do the spring part later. We can just bring that in little later. So that will require additional time, right? So let us first calculate what will happen after the collision. So after the collision, I'm going to assume that this 9 is going to move with some velocity v1 and that fellow is going to move with velocity v2. Okay, so this is the first one, this is the second one. So this 9 and that 9. So this is A, B, C. This is also A. So after it has collided, it is now continuing to move with v1. Okay, now let us write momentum conservation. Momentum conservation for this, initial momentum plus this guy's initial momentum. What is this? 9 into 6 plus 0 must be equal to 9 into v1 plus 9 into v2. 9 into v2. So you can see that the 9 can be cancelled out. So you know that v1 plus v2 must be equal to 6. So this is the momentum conservation statement. But we still have not used the coefficient of restitution, right? So we've got E minus E must be v2 minus v1 by u2 minus u1. v2 minus v1 by u2 minus u1. So that's 0 minus 6. So minus 6 into minus 1/3, when you take it there, you will get plus 6/3, which is 2. So that means v2 minus v1 is equal to 2. So if I add this up, you can see that the v1 cancels out. So you end up with 2v2 is equal to 8, or v2 is 4 meters per second. You can use this to calculate v1, but I'm not interested in that because this is 4 meters per second. This is immediately after the collision. What is this guy's velocity? If you calculate that, you will get 4 minus 2, 2. So v1 will turn out to be 2, but that is not important for us, for this problem. Okay, you can calculate it if you want. So now I've got this part. So we have finished till here. But the question really asks us to find maximum compression of the spring. So how will I find maximum compression of the spring? So what will happen at maximum compression? Now this v2, this 9 kg is moving, and as it moves, the spring will start to get compressed. And because the spring gets compressed, it will push this fellow, it will push that fellow. Okay, next lesson we will spend a lot more time looking at such kinds of systems of particles. But finally, because it's going to push that one and this one, you will find that both have to move with the same velocity, y. Let's argue y. This is also 9 kg, that's also 9 kg. This is B and that is C. Both, I am claiming, will have the same velocity v at maximum compression. Let us see. Now initially this guy has 4 and that guy has 0, so the spring is getting compressed because this guy is moving 4. So this fellow would have moved 4, this guy would have hardly moved anything, right? So that means the spring is getting compressed. But because the spring is pushing, this will become 3 and that might become 1. So in that case what will happen is this guy will get to 3, but that will move away 1. So when will the spring not increase anymore? When this fellow's movement and that fellow's movement, they are equal. So now they are equal. After that the spring is still pushing. So this guy is slowing down and that guy is speeding up. So then actually what will happen is this will move 1, let us say, centimeters. This is going to come and move only 0.8 centimeters. So the spring will start to extend back. So maximum compression, the velocities have to be equal. But you can treat it like a collision problem. The total momentum of this system must be equal to the total momentum of that system. What is the total momentum of that system? 9 into 4. So the total momentum in the beginning is 9 into 4 plus 9 into 0. Total momentum of this is 9 into v plus 9 into v. What happened to the spring? The spring has no mass, no momentum. But the spring was exerting a force here and exerting a force there. The impulse exerted by the spring on both sides is equal. So overall external impulse is 0. So it is exactly like a collision problem. So this is 18V. 9 into 4 is 18V. So if I divide the 9 out, you will get 2V is equal to 4. V is equal to 2 meters per second. But you expect that that's the answer, right? You expect that V must be equal to 2 meters per second. Why? Because both are 9, 9. This was 9 moving at 4. It is now shared between these two fellows. Both are moving at 2, 2. That's not yet over. Because what have we calculated? We have only calculated the final velocities. But the energy after the collision, during this collision, when you had this collision that happened here with E, coefficient of restitution 1/3, there was a loss of energy. So if I now look at the kinetic energy of this object in the beginning, okay, so kinetic energy of A is half into 9 into 6 square. So this is some 9 into 18. Okay, we won't calculate the value, but you will see that this is a lot of energy that was there. After collision, if I look at this energy with the speed of this fellow was 2, right? If you calculate that this was also 2, because you put 4, you will get 2. Calculate this energy, calculate that energy, the sum total, you will lose energy. When you have it's not a perfectly elastic collision, it's in fact a partly elastic collision. So you will have a loss of energy at this point. But after the collision is over, when this is moving, there is no loss of energy. There is loss of kinetic energy, but then that has become spring energy. Whereas this fellow, when the collision happened, part of the energy became heat energy. Heat energy we cannot figure out because we don't know what the formula for it is. But for spring energy, we do know the formula, right? So what is the energy after collision? Half into 9 into 4 square. Okay, so if I write this, it's 8 into 9. So I'll write it as 9 times 8 joules. So this is kinetic energy. This is kinetic energy before it starts, but this is after the collision. There is no spring energy and there is no energy for this fellow. So therefore, this is the total energy immediately after collision. Now, let us say kinetic energy for maximum case is you have this fellow's kinetic energy plus that fellow's kinetic energy. How much is that? It is going to be half into 9 into 2 square, but plus half into 9 into 2 square, so 2 times. Right? So this is going to give me how much? 36, 9 into 4. I'll just call it 9 into 4 joules. So the kinetic energy has changed, but this was the one at the beginning when you started the compression of the spring. This is when it is maximum compression. There the spring energy at when the situation was like this, just after. So this is not A as in this object A. This is after collision. So I'll call it AF. Spring energy immediately after collision is 0. Spring energy for maximum compression is half K is 32 into x square. This total must be equal to that total. So if I equate these two, you can see 9 into 8, 72 must be 9 into 4 plus 16 times x square, 16 times x square. So once I have figured this part out, then we can bring everything to this side. You will see 9 into 4, 9 into 8 minus 9 into 4 is 9 into 4 by 16 is x square. So x must be root of this. We can cancel this out. This is 4. So root of 9 by 4 is 3 by 2 or 1.5 meters. And so the maximum compression of the spring x max is 1.5 meters. Let us quickly summarize what we did. First, we did the collision part with coefficient of restitution. So that gave us, you use momentum conservation. You can't use energy conservation, but you can use coefficient of restitution, right? So we use that to find out the velocity of this fellow. After that, from here to there, when this whole thing was getting compressed, we used momentum conservation to find this velocity. And then for this period to this period, we said the total energy must be conserved in the forms that we know. Total energy always conserved, but in the forms that we know. For example, spring energy, kinetic energy. So we use kinetic energy in the beginning plus spring energy, which was 0, must be kinetic energy in the end plus spring energy, which is non-zero. So the spring energy then gave us what the maximum compression of the spring should be.